Alright, guys. Chapter 7, which is the last chapter you have homeworks for. So, yay! Well, those aren't just hands. These are just hands. So, this is where we going to talk about estimating. And as much as I would love to crack through chapter 8 with you guys, I have an odd feeling that by now most of you are done, and considering that the semester is going to be over in like soon, let's knock this one out of the park. Chapter 7 is not very difficult chapter. It has presumably 4 sections, but really has 2 sections in it, and those are relatively straightforward. So section number 1, numero uno, is dealing with how we talk about population parameters using sample statistics with a level of certainty that allows us to say, hey, this is happening or this is not happening. This is very useful when we have smaller samples than the whole data set is. Exit polls, for example, we ask a couple people what they think and how they voted, and suddenly we know who's winning the election without actually doing the voting count. Now, we should do the voting count, and I'm not advertising not to do the voting count, but I'm saying we actually have a very good idea. And so to think about it is, if how do I say it? Imagine you went on a Tinder date last Friday, and there was tequila. And again, I'm not advising to drink tequila, personally not my drink of choice, but say tequila. And you come back to your house, and your housemate or your friend or your family member goes like, hey, how tall was the other person? And so you being you, right? That's you, right? Talking to your family member, and that's them. By the way, I hope you guys appreciate the non-gender, race-specific stick figures, and this is as good as quality drawing I can do. And what do is you take your hand and you wave it somewhere between, be like, oh, they're about knee high, they're like, how big is that part that you need to fix your engine? No, it's about E big, right? We tend to say things like this, or how many people were there at the club? About 50, right? And we say those things, and what we are producing is this kind of a spatial arrangement, and in our case, a set of numbers that supposedly encompasses this. But if you had a housemate like myself, I would be like, can you be more specific? Well, then people would say, hey, yeah, it's not E high, it's E high. Just making this thing smaller and smaller and smaller. But then if I kept on pushing and say, hey, on a scale of 0 feet to 10 feet, how tall was your date? Specifically, and you say, this, right? You say 4'11", again, true or not. How sure are you that they were actually 4'11" versus this, right? You seemed pretty confident that they were about the tall stuff, right? But if I ask you for a specific number, you're like, there's some low confidence that it's right here. And there's higher confidence it's actually there, right? And this is all chapter 7, first part of chapter 7 is all about, is toying with those two things. How big of a range are you producing? Like how sure you want to be? If I want to be absolutely sure, I guess the height of your date, right? I'm going to say they were probably between 0 and 10 feet tall. maybe I'll make it 11 just for good measure. And then I can be 100% sure that your date was somewhere here. Right? So this is a very wide range. But if you ask me if they were between 411 and 52, this is much more precise. But am I more confident about it? No, I'm less confident, right? Because I could have made a mistake. The music was loud, there was lots of tequila, we were dancing, I was twerking, they were twerking, just kind of this thing. So I'm not sure of this height. And this whole concept of how sure are you and how much are you giving yourself. And why is this important? Well, because the actual height of this person is somewhere on this line, right? Is somewhere here. And the question is, how much of a margin of error are we allowing ourselves to have to deal with this, right? So if you take a look at page one. If you take a look at page 110, you have a very pretty graph talking about exactly that. Now again, in this case, we're talking about a single point, but if I asked you about the average of your Tinder dates, I could have done the same thing, and that would probably be a bit more matching. But the idea is there's a point estimate of in your mind how tall people are, for example, and then you give yourself wiggle room, right? Or how many calories did you eat for breakfast? I ate about 800. Did you eat 800? Was it like 790 or 805? Right? Again, you have an idea in your head where it is, and you give yourself a little wiggle room, right? This concept of specificity becomes problematic. Why? Well, because the only way we can make statements about a population parameter, say population average, is if you run the census. And a census is you go out and you check every single piece of data. And that is a problem. And the problem with that is there's a lot of it. So here's an example. Let's make it overwhelmingly big. Yeah. All right. Alright, ready for it? Are you ready? You sure? No? Maybe? Okay. What's the average roll of all the dice? You didn't get it? Okay. How about now? What's the average roll of all the dice? Well, you could go out and count every single one and run a census. The problem that gets big. How big? Well, think about the census the United States is running for population. What are we? Population 315 million people in the United States, right? The census takes months. They have to hire 80,000 people, go and knock on doors, and this is problematic for small samples, like small populations, like the number of dice. That's tedious but doable. But imagine if I had a truckload of it and I just kind of crushed the truck and the dice spread everywhere. And I ask you about the average roll on all of those dice. What happens if you don't find all of them? You're missing 5%, right? It's not a census. It's a large sample, right? So what we do is we take a sample. And we figure it out. So if we take a sample average, in this case, that's what? 13 divided by 3. So that comes out to be what? 4 1/3. And that's our point estimate. This is the best estimate we have for what's in here. And that's the only one, right? Okay, so that's our estimate. Now question is, how precise is this estimate? Okay, maybe it's something here. And what we are actually trying to figure out is where the actual average is. And we want to guess that the actual average, somewhere inside of this, we find the mu, which is what? Well, which is the population parameter, the population average. And we figured, hey, it's somewhere here. Well, how big are those? Well, this is plus E, this is minus E. So if we were to say, hey, our margin of error is, say, 2, right? If we calculated our margin of error to be 2, and we're going to do this in a second, then our estimate will be from 2 1/3 all the way to 6 1/3. We could be pretty confident what we wrote here as an average is going to be somewhere here. This is high confidence. On the other hand, if our margin of error was 1/3, which means we are very specific of where it is, our confidence interval would be somewhere between 2 and 2 2/3. Sorry, 4 and 2/3, right? And that's a very specific one. And our confidence would be low. Right? And again, what we do is we take a sample, and based on how confident we want to be, we produce a kind of an estimate of it. Now, the actual result, well, the actual result looks a lot lower. Does it? 3. And there's a bunch of 3s. There's a 4. Bunch of 5s. There's another 4. Bunch of 5. Bunch of 6s. There's another 3 and bunch of 5s. Let's see what the average came out here. So we have 6 1s plus 4 2s plus 5 3s plus 2 4s plus 7 5s plus 5 6s. And we have 5. We have 5, 10, 15, 20, 25, 25, 29 dice. So that's the actual average that came out from our roll. Now, this number is different than ours. Again, this is an estimate. This is not the actual value. This is an estimate because it was taken from one sample, right? And again, if we picked high confidence, 3.5 would end up somewhere here. If we picked up low confidence, we got here. Well, what does mean low confidence? Well, it means the probability it's going to end up here is small, and the probability it's end up out here is large. High confidence, probability is going to end up in the middle, high, and small confidence it will end up outside, which produces this concept of once you have this sample estimating the population, we are no longer saying 100%. The only way we can say 100% is if our sample equals our population. In that case, there's 100%. But anything short of that, we cannot use 100%. We use numbers like 90% or 95% sure, right? And this estimation, this confidence level, needs to be included every time we're saying, hey, it's about E big. How sure are you? I'm 90% sure. Right, so this is the basic concept of this. And again, it works both for means and proportions. So let's get into the examples and do the easy stuff. All right. So, and for those people that are OCD, I'm just going to clear this up so we don't have to look at all the dice. All right. So example number. Take a look at the picture 7.2 with the simulation of 40. This will show you when we took samples, that each sample will suggest a slightly different confidence interval. But example 1. Find the number z alpha over 2 needed to construct the confidence interval. Well, so what is z alpha over 2? Oh, I cannot speak today. I thought yesterday was bad. All right, z alpha over 2. Z alpha over 2 is a critical value that separates. So this is a critical value that does what? Well, that separates the likely versus the unlikely regions. Well, what does mean likely versus unlikely? Well, it means the following. If we build something that looks like this, right? And we say, hey, this is the likely region. And those are the unlikely. This is the likely region, those are the unlikely regions. And somewhere here, there's z alpha over 2 and z alpha over 2 with a minus. Right? And again, it's very much like what we did here. This is the likely region, these are the unlikely regions, right? Same here. This is the likely region, and everything outside is unlikely. Same thing here. Likely, unlikely. Likely, unlikely. Right? So all those things are just talking about this. So what we have usually, what's the convention is to how to talk about it is we have a confidence. We have a confidence level, and we define it as 1 minus alpha. That's how we define it. So we have a confidence level, and confidence level tells us how big this inner space is. So that's our confidence level. The unlikely region, both this one and this one, are symmetric. So alpha, right, is corresponding to both of those. Now this and this are both alpha. Well, alpha is responsible for both. So how big is one of those pieces? Well, they're symmetric, so they're the same size. So if the whole thing is alpha, one of those has to be alpha over 2, and the other one of those has to be alpha over 2. So alpha over 2, right, is the size of this tail. And so z alpha over 2 corresponds to the z-score attached to those tails, right? Again, our table, the ones in chapter 12, I attached it in a separate format, but any table, z table. What we have in our table is we have something that says, hey, if the z-score attached to this, right, alpha over 2, so this is alpha over 2, Right? And why am I saying negative? Oh, because this number is going to be negative. So negative of a negative number gives me positive. So this is this whole concept. So now if it says confidence of 90%, so if we have confidence level, right, 1 minus alpha equal 90%, if this is 90, then both of those have to add up to 0.1. So one of them adds up to 0.05 and the other one adds up to 0.05 as well. This is our confidence level. Well, so what is the z-score here that corresponds to this area? Well, if we look up 0.05, if you look up 0.05, and again, this is probability, so we're looking in the meaty part of the table. 0.05, 0.05 is right here, and that's negative 1.645, which means that the one on this side is symmetric, 1.645. Now, if you if you take a look at the appendix attachment on page 706 and 707, you will find the critical values for t. Now, let's not worry about the critical values for t just yet. Let's get to page 707. So on page 707, at the bottom of the table, and you're gonna have to zoom out or zoom in if your eyesight is really bad, you will see, let's see, hang on. Yep. You will see this. Oops. Actually, let's make it. Just going to. You will see this. So that's page 707. And if you look very closely right here on this column corresponds to, scroll up, 5%. Now, I'm going to explain how to get there in a second, but just bear with me. So there is the table that shows up in some of the questions. This is the table. Anyways, so let me explain how I got this. Alright, so you can, every time you have to do with the z-table, you can just look up this in the meaty part of the table and find the z-score, and you can get this. Now, because 5% is one that is commonly used, we gave that an extra decimal place, but that's, there's extra information, but that's how you get this. And again, this part right here, well, the z-score corresponding to this split, again, z-score doesn't correspond to a specific area. In the table, the z-score is calculated using the area to the left, but we can get the z-score just by looking the area to the right as well. Just this is 1 minus the area to the left. Alright, so for 1 minus alpha equal to 90%, z alpha over 2 equals to 1.645. So that's this. I need more screens. All right, so that was part A. Part B. For part B, we have 1 minus alpha equal to 99%, which is 0.99. We draw a picture 0.99. Somewhere here we have our alpha over 2. Alpha over 2. How big is alpha over 2? If both of those are 1%, then each one of those is 0.5%, so 0.005. Okay. And so if we look up 0.005, again, in the MIDI part of the, because this is probability and what we're looking for is a z-score, 0.005. That's negative 2.575. So z alpha over 2 equals to 2.575. And again, this is the second very common percentage, so we give it one extra decimal place. Now, some books and some tables will give it as 2576, and again, those numbers aren't different enough, and this class isn't stringent enough about it to cause you problems. But some tables will actually give you a little, if you can see it, confidence levels, and they actually give you some of the basic ones. Some won't, some will just be a regular table. The one in the appendix is just a regular table, so you just have to do it. Otherwise, you can just look it up somewhere else too. So that's the basics of it. So we got the z-scores, check. That was example 1. And I'm long-winded, and this is already what? We're at 30 minutes and I'm still talking about example 1. And I said this is an easy chapter. I lied again. It's okay. The semester is almost over. Example 2. Find number z needed to construct the confidence interval when All right, so example 2. Example 2 says, hey, rather than using this table, let's use the table or the figure 12.3. And again, if you look at 12.3, what you have on top you have some description saying, for example, that. And if you scroll down, there's some df here, some bunch of numbers here, and then eventually you get to infinity z, and you are going to get 1.645. So that's what table 12.3 says. And what it actually is saying is, hey, there's this critical value t, which again we're going to cover it, I think, in example 5, but we're going to cover it in a second. T, for now, let's think about t the way we would think about a less precise estimate, and so let's leave it at that. But if the estimate is infinitely more precise, then we are talking about z's. So what we are saying is, if we have z alpha over 2, and alpha over 2 is 5%, so this is 0.005, then for degrees of freedom going towards infinite, which is the last row, t 0.05 equals z 0.05, and thus this number becomes our number here. So that's just saying, hey, there's a shortcut to looking things up on the table. And again, if you know how to look things up on the table, it takes half a second, and if you've been doing problems for a while, you just remember those things. Again, this is a 6 weeks course, so let's not go all crazy about memorizing things. So let's just follow. And again, if you look up the table, this is the bottom, right? So you have the df, degrees of freedom on the side, and then what you're looking for is this. And then if you look couple rows over, there's 5, 2, 5, 7, 6, and that's this one. 2, 5, 7, 6, and that's this one. All right, so that's example 2, and let's not worry about it. Example 3. Oh, finally some numbers. Yay! I was waiting for numbers. All right, so if we have a sample size, so this is example 3. We have a sample size of 49 with a mean of 35 and a sample standard deviation of 14. So far everybody's with me. Construct a confidence interval. So what we're looking for is a confidence interval at 98% for the population mean using this information. Interpret the meaning. Okay, so how do we construct a confidence interval? Well, we know that we're going to take our sample and we're going to allow it some wiggle room, and this wiggle room is allowed to us by a margin of error. And margin of error is how confident we want to be, right? Because we realize that if we want to be more confident, our margin of error, right, our critical value is going to skyrocket. If we want to be less confident, it's going to get smaller, right? So this times how the data is kind of tossed around, divided by sample size, right? The bigger the sample, the more precise we are, right? The average of dice rolls here, if you have 1 die, that's not very good. But if you have 5 of them, and you have an average of those, now we can start talking about all the other dice. So this is the basis. Alright, let's find z alpha over 2. Well, so, and again, if you notice, I have a tendency to draw pictures everywhere. So this is 1 minus alpha, so we have 98% in the middle, which means that this is alpha over 2, this is alpha over 2. If this is alpha over 2, then this has to be 1%, right? Because there's 2% to be split into 2 pieces. This is this. And so what we're looking for is this number. 1%, 0.01, ladies and gentlemen, is right here. And that makes it negative 2.33. Again, negative, negative. So our E is 2.33 times 14 divided by square root of 49. So our E ends up being 2.33 times 14 divided by square root of 49. 4.66. Now again, I know the solution to example has this number 2.326, and yes, you can use it. I use either one works, and again, that's why I'm saying it's more about you understanding how to get there rather than precise numbers, because when you get to precise numbers, you're going to have an actual program spit those out numbers for you. You just need to know where if you got it right in the ballpark, right? How confident you are that you're getting it right. And so what is our thing? Well, our thing goes from this number to this number. So how big is x minus e? Well, x minus e is 35 minus 4.66, and x plus e is 35 plus 4.66. So this ends up being 30.34, and this ends up being 39.66. Again, no decimal places. We're probably going around this. So what is this saying? Well, this is saying the following: we have no idea where the population parameter mu really is. We don't know. Now, how do we know? We don't know. Well, we didn't run a census. We just took a sample, right? So maybe I should write it out. And by what it really is, I mean the value of it. But we are 98% sure that its value is between 30.3 and 39.7. Right? This is the whole concept of estimation. I have no idea where it is. And I'm either too poor, too lazy, or incapable of producing a census for it. But what I can do is I can take a sample of 49 things and say, hey, I have an estimate, and the estimate is somewhere between here and here. How sure am I? 98%. Now, could it be that the population mean, right, that the mean is somewhere outside of this? Yes, there's 2% chance it's going to be outside, but this is as close as I can get it. I'm 98% sure this is going to be here, right? Again, if I was going to be 90% sure, then this range would shrink. Why? Well, because instead of 2.33, we would use 1.64. So if you want to be less confident, 90% confident, this thing shrinks. If you want to be more confident, 99% confident, then this thing expands. So the more confident you are, the larger range you need to give. And so we run into a problem of dealing with it. But that's a problem for another example. Let's take a look at example number 4. Ooh, GPA. Perfect timing for the end of the semester. All right. So example 4. A random sample of 120 students. Now, again, I appreciate that those are large samples, right? They're 30 or above. So, of a large university has a mean of 2.71. That's not great. Average. Oh, all right. S is maybe it's one of them party schools. And a confidence interval of 90%. Confidence level, but confidence interval at this confidence level. There's a bunch of ways I will write it, and most of it are bad habits. So, all right. So we have this, and we want to find the confidence interval. So we want to find this. Well, first things first, I'm going to deal with that. If this is 10% split into two ways, that's 5% here. It's negative z alpha over 2, and that's going to end up being negative 1.645. How do I know? Well, first of all, we did it about 7 minutes ago, so we got this already. Second one is I've been doing it for a while, so I have this somewhat memorized. Third thing is if we look up 5%, it's going to be right here at negative 1.64. So that's done. All right, so now our E is Z of over 2 s divided by square root of n. So in our case, it's 1.645. 0.51 divided by square root of 120. So let's see. 1.645 times 0.51 divided by square root of 120. Boom. 0.07. I have 2 decimal places here, so let's call it 7. It's actually, for those who are curious, 766, but I'm just going to estimate it at 0.077. And so now our confidence interval is 2.71 minus 0.077 to 2.71 plus 0.077. So this comes out to be 2.787, and this ends up being 2.7 11 or 10 minus 7. It's 2 2 3. No, that doesn't look right. My brain's not working. I apologize. That's embarrassing. Okay, so this is 2.633. All right. Too much statistics. So we have those two numbers. So what's the answer? Well, we don't know what the GPA for this university really is, but we are 90% sure it's somewhere between. Oh, sorry, I made it wrong. This is plus. But we are 90% sure. So confidence interval at 90% is 2.633, 2.787. We don't know what the population GPA is, but we are 90% sure it's somewhere between 2.63 and, right, because this is about 2.63 and 2.79. Right, so we are 90% sure nobody has a 3.0 on average. Like the university doesn't have a 3.0. Right? Individuals can have above and below, but as a whole, because we are talking about the mu, right? Estimation for the mu. So we build this thing and we get this. All right, easy, I think. And that's it for the first part. It's a simple formula. Now here comes the problem, and here's the problem. If we have a large sample, we can do this relatively confidently. But if we have a small sample, we run into major issues. And some of the major issues are, well, it's a small sample. It's not very reliable. Right? We always had the problem with that if we took small samples, things are not necessarily lining up with everything else, right? If I took 4 of your grades from the whole career as a student, they wouldn't very well give your current GPA, would they? If I took 50 grades from different classes, starting from high school and maybe middle school and now, they will give me a much better kind of view of what your grades look like. Not who you are and how good of a student you are, but what your grades look like. Right? Again, if you want to test drive a car, you don't drive it for 50 yards. You want to take it for, maybe half a mile, maybe a couple miles, right? You want to get this feel. And the problem is somewhat simple. And this problem plagued this small company. I don't know if you heard it. It does craft beers called Guinness. I don't know if you ever heard of this company that makes beer called Guinness. But there's this company in England that made Guinness, and then they had a problem, because if they wanted to talk about certain things about their beer that they made, and they want to take a large sample, means that for all sex and purposes they needed to open almost every single keg and every single barrel and every single bottle. And I don't know about you guys, but if I'm getting a beer, I don't want a second tasting. Like, I don't want a beer that somebody else licked for all sex and purposes, just so they can get a good estimate, right? So how do you deal with it? So then one of the workers at this company devised a method of doing statistical analysis on the beer without opening all the beer bottles and beer kegs. Now again, you can Wikipedia this and get the actual story, but I'm paraphrasing here and embellishing it as I go along. And so he did that, and it worked. And like with any other big company, the company would probably keep it as a patent or hidden somewhere as a secret. So what the guy did is he published it under the name Student Tea, and that's why we have tea distribution from that. So the Student Tea is the guy that decided to share with the world how to do this. So that's this. Now tea has one important feature, and the important feature for tea is that if we have a tea distribution and we take our N and we start climbing it, right, closer and closer to big N, as in we take a bigger and bigger sample, not necessarily reaching a census, but the closer we get, T starts looking more and more like Z. For a small N, T is bigger than Z. For a small N, T is bigger than Z, right? Because T has to overestimate things and give itself a lot more margin to be the same level of confidence with Z, right? If you here's an example. If you dated 100 soldiers, you will know what to expect from date number 101. But yeah, you could go wrong. You could, date somebody who's completely different than the other 100, but you would get a general feel for what's going on, right? Deployment, for example, how that feels. But on the other hand, if you dated only one soldier or 5 of them or 2 of them, right, your expectation level of what you know this is going to be like versus what it actually is like is going to be off. So you're going to be overestimating how things impact you, right? If you always drove a scooter and suddenly you get a high cc bike and you crank the throttle, this is the first bike you drove, motorbike that you drove, you always should have extra caution, right? You buy a sharp knife and you never had a sharp knife, you're gonna cut a little slower. You never used a power tool, you buy yourself a handsaw, and suddenly, you're not gonna crank it up to 100, right? You're gonna go slow and try to get acquainted with it by increasing your exposure, right? So this is what Student T does. It allows this. So if you look at at if you look at the table, right, critical values for T, right here on the left side, you have something that denotes DF. Well, so what is DF? DF stands for degrees of freedom, and that's defined as n minus 1. Now, how can you wrap your head around it? It's very simply. We have three markers. Well, hang on. Here you go. We have three markers. How many choices do you have to pick a marker? No, most people say 3. Okay, pick one. How many choices do you have now? 2, right? How many choices do you have now? We don't have a choice. 1 is not a choice. So what you really have is you have 2 choices to be made. First and second place, because the third place is implied. Same thing if you have 4 markers. You have only 3 choices. 1, 2, 3, because the last one is implied. Same thing if you have 4 markers. Right? 1, 2, 3, 4. Because the fifth one is implied. Right? Having one choice is not having a choice at all. So that's here. Let's see. All right, so let's take a look at it. Sample size of 15. What does it mean? A small sample, right? With a mean of 35. A standard deviation of 14 and a confidence level of 95. So what do we have? Well, we want to find this, but now our E is that. Why? Because we have a small sample, so we want to overestimate the critical value here, the parameter here. Alright, well, so what's T alpha over 2? Well, that's really T, half of what's here. So what's alpha? Well, alpha is 5%, right? Because this whole thing has to add up to 1. So alpha is 5%, so T alpha over 2 is T0 2.5%. So now we look at a t-table. Do I have a t-table here? Yes, I do. We look at a t-table, and what we're looking for is df of 15 minus 1. So df of 14. So we look up df of 14, and we're looking for a tail that is 5%. And I got, sorry, not 5%, 2.5%. And I got that. Now let's find it on the table. So here you can see. Right, so that's our table. 2.5% is right here, and we scroll down. 2.5% df of 14 right here. 2.5% right here, and so our number is right here, middle of this middle bottom of the screen, right? 2.5% again. It says T alpha because it's looking for one tail. We have two tails, so this is alpha over 2, this is alpha over 2. This number is corresponding to alpha over 2. And then df is 15 minus 1, 14, right here. Alright, so we got this. I'm gonna switch everything. Alright, we got this. So our E equals to 2.145 times S, which was 14, divided by square root of 15, right? S. And this comes out to be 7.75. Yeah, so what is our answer? Well, 35 plus minus 7.75. So this is 42.75, and this one is minus 8. So that's 27.25. We don't know what the population mean really is, but we are 95% sure, right? 95% sure that it's somewhere between those two numbers. Alright guys, if you don't mind, I need to take a 2-minute break. So I'm just gonna put you on a pause. I'll be right back. Sorry about that. I ran into a slight problem where everybody wants something, and because of COVID and whatnot, my family unfortunately takes priority. So you guys get put secondary. Sorry. I love you all, but between you and mom wins. All right, example 6. I'm happy to report everything is okay. So, sample of 12 students, n equals to 12, average equals to 2.71 with a standard deviation of 51, 1 minus alpha at 90%. Construct. All right, so again, we look up 90, which means alpha equals to 10%, which means alpha over 2 equals to 0.05%. Sorry, 0.05, so 5%. So if we look up 5% is check, and then our df is 12 minus 1, right, because it's n minus 1, and that comes out to be 11. So our t alpha over 2 is 11, and 5%, I get 1.796. All right, let's see if we can reproduce that. This time around I'm going to use the other table that I gave you guys to work with, so I'm going to give you guys this one. Same idea, it's a t table. All t tables behave the same way. And what do we have here? We have, can you zoom it? No. All right, we have 5%, so 5% is right here. Now this one has a lot of things here and a confidence level. So at the bottom of it, you have a confidence level, which makes it things easier, right? And you have the z-score right here attached to it. So, but on top, you have a couple things. First of all, you have t of 95. What does mean t of 95? Well, this means that if we were to graph this, right, and this little section is alpha over 2 at 5%, if this is the alpha over 2 at 5%, right, then all this area right here is 95. Why? Because this is 0.9 and this is another 0.05. So what this is saying is this t alpha over 2. And this t alpha over 2 is, is of 5, here, 95, right? Is with one tail of 5% or both tails at 10%. So you just have to be careful, and each table has something different. So this table has that, where this table, right, just gives you this one tail. And again, 5% at 11 df, right, 11 degrees of freedom, 1796. If we look at the other one, 5%, right, or 90% confidence level, right, or 10% for both tails at 11 is 1796. So all tables are looking exactly the same. Cool. So this is that. So this is that. All right. So now we have this. Let's calculate the E. E is t alpha over 2 as divided by square root of n. So that's 1796. 0.51 divided by square root of 12. And again, this is n, this is not df, so you have to be careful. And let's plug it in. 1.796 times 0.51 divided by square root of 12. So I got e of 0.26 4. So x bar plus or minus e, what do we have? X bar plus e is 2.974, and x bar minus e is 254.4 this is going to be a 4 and that's going to be a 6. We don't know what the population GPA really is, but we are 90% sure it's somewhere between those two numbers. Let's see, I thought we did the GPA one before. Yes, we did. We did the GPA one before. See the difference? This is what we got before, this is what we have now. Sample size 120, sample size 12. So, so big sample, small sample, and the difference, right? This is a lot wider. Why? Well, because our sample is much smaller, and because we have to use the t versus the z critical value. But I thought it was just kind of cool. So right, so that's example 6. All right, example 7. Oh, I'm gonna have to fix that. Page 117. On page 117, it's missing a parentheses. The formula is missing a parentheses. All right, I'm gonna fix that later. Example 7. Now we're talking about proportions, and proportions aren't the way we deal with proportions is not much different than the way we deal with means. You just the formula is slightly different, but overall it behaves the same way. We still have kind of a p hat, right? Sample proportion plus or minus some e, and this time around we define the margin of error as z alpha over 2 p hat q hat divided by n, right, where q hat equals to 1 minus p hat. So we have this very simple kind of a cute formula to deal with. So question is estimating the of large college of female random sample of 120. X is 69. And there's the confidence. Why they write X? Well, because we want to see how many females are. So every female that we have in our sample would be considered a success. So this is this. P hat is X divided by N. So in our case, it's 69 divided by 120. That's 0.575. So we have that. Q hat would be 1 minus P hat. So that would be 0.425. right? That's my confidence level, which means that alpha over 2 here is, well, let's see what alpha is. Alpha is 0.1, so alpha over 2 is 0.05. We've been doing this for a while, so we know that this is that, 1.645. So we can calculate our E, and our E becomes 1.645, right? Z over 2. P hat, 0.575 times 1 minus P or P hat or Q hat, 0.425, divided by 120, right? That's our sample size. So let's see, 1.645 times square root of 0.575 times 0.425 divided by 120. Not divided by 120. And we got our E to be 0.074. And so what is our confidence interval? It's p hat, which is 0.575, right? P hat plus minus E. So it's our p hat plus minus 0.0742. So what is that? That's 0. I'm just going to be lazy here. $5,008 to 0.6492. I'm not sure what the population proportion of females at this college are or is, but I'm 90% sure, right? 90% sure it's somewhere between 50 and 65%. Boom, shakalaka. All right, that was cool. All right, now we get to the last little bit of chapter 7. There is 4 examples here, and here's the skinny that doesn't get touched up on enough in statistics. Surveys. Most of the data we collect is from some kind of a surveys. The problem with surveys is that aside from the fact that they take time, they cost money. And if you're lucky, a survey will cost about, 15-20 cents per survey. If you're unlucky or you want extra statistics done, those surveys get expensive, and we talk about $70 per survey. Now, $70 might not feel like a lot, and $20 might not feel a lot, but consider this: usually about 10 to 20% of people reply to surveys. Sometimes as low as 5% will reply. How many surveys did you get in your email or your mail? People send you stuff and you're like, I'm just going to toss it, rather than actually sit down and fill up the survey, right? You probably filled up your census and maybe some your recycling things for the city, but that's about it. You don't fill surveys. And there's ways to convince people to fill out surveys. For example, you ship a survey with $1, and then people feel more obliged, or you have pre-stamped envelopes, and there are other classes that teach you how to do this. But surveys are expensive, which means that the difference between sending out 1,000 surveys or 10,000 surveys is a lot of money. Again, think about a survey that costs $50 per survey. Sending 1,000 surveys, that's $50,000. If I have to send 9,000 surveys extra because I don't know how many surveys I have to do, I'm sending almost what? I'm sending almost $450,000 extra money on something that I actually didn't need. Right? So surveys are important. So it's very important for us to understand how big of a sample do we need to get to manage our expectations, our margins of error. And so this is what we're going to do in 7.4 is we're going to look exactly at that. So we're going to start with example 8. And in example 8, and I'm going to be talking while we go through it, is saying, hey, I definitely, absolutely, and overwhelmingly want to be 99% sure. And you usually get that requirement from the type of survey you run, or the company you run, or the requirement for the grant money, or the city, or any other reason. So you get that from somewhere outside. Or you make the determination yourself based on the previous data. So how sure you want to be is somewhat specific. I know for a fact in the military, when you test equipment, this number is extremely important. Second thing that you're going to get is you're going to get forced an E, in this case 0.2. And that's the margin of error. And you're going to be forced that. Right? If you're talking about elections, most of the time when you talk about elections, what do you see? Well, you see that somebody's popularity is 35 plus minus 1%. There's your E. There's your P hat, and there's your E. This is forced on you. Right? In all those other cases, our E's weren't exactly nice numbers, right? So we can force this number. And what we're saying is we don't want the margin of error to be this. We want the margin of error to be at most this. And that's a implied thing. Like if you do it and your margin of error ends up being 0.1 versus 0.2, brilliant, we're even more precise than we implied. But 0.1 is going to cost us a lot more than 0.2, so 0.2 is kind of the limit. But if it goes below, and that's going to show up to be important in a second, we're okay with this. So just keep this in mind. All right, and we know that the population standard deviation is, well, if we're going to survey the population and we know the standard deviation, like what the hell? Like to know this, I need to know the mean, and if I know the mean and know this, I have access to raw data. Like how do we get this? You get this from general studies, larger surveys. Like for example, you can get this from a census, and then you can run this on a smaller subset of census, right? You can run your own sample to ask something else, so you can get those numbers from somewhere else. You can get it from a previous study. You can estimate it from somewhere else. So bound that having a sigma screams, hey, we have done a census, but mind you that we can get this number from other sources. So that's that. All right. So now we try to solve it, and the formula for that is that doesn't. How did we get this? Well, we went from here, right? Standard deviation, we have sigma, we use sigma. We have S, we use S. We have sigma and S, we use sigma. Sigma is more precise. So anyways, we get from here, right? If you take multiply both sides by square root of n, you're gonna get divided by e, right? Square both sides, and you get that, which is that. So this is the formula we're going to be dealing with. Now I prefer this one over this one because I just have to do square ones, but potato potato. So n equals z alpha over 2 for 99% means our alpha is 0.005, and if I look up 0.005, that's 2.575 or 76, so that's 2.576 times sigma, which is 1.3, divided by e, which is 0.02 squared. So 2.576 times 1.3 divided by 0.2, and we square the whole thing, and I get n equals to 28306. So how many people do we want to survey? If we want to survey this number, you're wrong. If you want to survey this number, you're wrong. That's not the answer. Why not? Well, because this means you're going to send the survey to 280 people and 36% of a person. Yeah, I don't... 36% of a person is a head, a leg, and a thigh. Do you keep your ex-girlfriend in a freezer or something and she's still alive enough to, like, are we talking Walking Dead, zombies, Frankenstein, you know, like Alida, like, what the hell, right? 36% of a person is not a person. So what we do is we round this up to 281. Why? Because 36% of a person is not a person. And this is not a fetus abortion conversation. No. This is just 36% of a person is not a person. Like, how many people live here? 2. Can I see the other person? Well, here's the head, here's the arm, and here's the thigh. What's wrong with you, right? Anyways, back to normal people world. We round up. Now here's the skinny. If we round this up, right? This is the minimum we need to ask to get 2%. If we round this up, this number is slightly higher, which means that if we do this calculation, so if we take this number and we plug it in here, we get an E that's going to be slightly lower than 0.2. Slightly lower. If we round this down, we're going to get an E that is slightly higher, right? Because it looks like this. If as n goes up, E comes down, assuming the sigma and z alpha over 2 are the same. But if n goes down, E goes up, right? And what's important is that this is an ironclad requirement of your work. You want 0.2 to be your margin of error, not 0.2002, 0.2. But Mr. N, if it's 281, then this is 0.1994 or whatever. Sure. Is it below 2? Good. Right? Is it above 2? No. Right? So this is this whole idea that what we're really looking for is this. But we know that for a fact if our E drops significantly, right? If our E drops significantly, then our sample size has to be a lot bigger. And if it has to be a lot bigger, it's going to be a lot more expensive. So that's 8. All right. That's 8. Let's see. 9. All right, 9. For 9, I'm feeling green, so we're gonna do green. For 9, we have 1 minus alpha is 95%. Then we have ISCOM estimation, great. Okay, so we have our E to be 1000, because that's within, right? Welders with at least 5 years experience within $1,000. Estimates the range of incomes is no more than 24. Okay, so using the empirical rule, he estimates the population standard deviation is 1/6 as much, or about 4,000. So we have an estimate for this at about 4,000. Is the 24 important? No, the 24,000 is not important, because the 24,000 says estimates the range of incomes is no more than 24,000. It's like, okay, great. That's not doing anything for me, because I need confidence level. Does my Z alpha over 2, in this case it's 1.6. Right? I need my margin of error, and I need some variation in the data. And so our N is Z alpha over 2 sigma E squared. So that's 1.96 times 4,000 divided by 1,000 squared. I'm going to cancel those zeros out. So it's 1.96 times 4 squared. And I come up with 61.47, which means our N is 62. Why? Because 47% of a person is not a person. And that's 9. Stuff gets easy and easy. All right, estimating P. And again, same idea. The formula. The formula got a little different, but Z alpha over 2 it's that. Right? Z alpha over 2 squared divided by E squared times P hat Q hat. Again, Q hat is defined as 1 minus P hat. Alright, so let's see. 1 minus alpha is 98% or 0.98. And the margin of error is E equals to 0.05. Now you have to be very careful when you're talking about proportions, because I could say this, or I could say margin of error, or within 5%, and then your E is not 5. Your E is 5%, which is 0.05. So you have to be careful the percentage not to do this. This is not 5%. Sorry, this is not 5. This is 5%, which is 0.005. All right, assuming no prior knowledge. All right, no prior knowledge. What's the worst case scenario? Again, back to Tinder. We're gonna pick on Tinder today. If you matched up with somebody who you find attractive, or George Clooney, right? If you matched up with somebody who you find attractive, and you knew that there's 95% chance that they will want to go out with you if you message them, would you message them? Right? Would you swipe right if they're going to swipe right? If you know for a fact they're going to swipe right, yes, right? If you find them attractive. On the other hand, if you found somebody who's attractive and there's no way they're going to swipe right on you, you know that for a fact, would you swipe right or would you just swipe left so the algorithm gets learned, right? This idea is that if you know for a fact you're going to win, you're going to buy the lottery ticket. If you know for a fact you're going to lose, you're not going to buy the lottery ticket. I'm assuming you don't have a degenerative gambling problem, right? This idea that if we know which side it is, it's easier, right? If you have one set of dice that always rolls a 1 and one set of dice that rolls a 6, and you play Monopoly and you need large numbers, you're going to pick up the blue dice, right? If you want to go far. They always roll high and the white dice always roll low. You're going to, but if you want to roll low, you're going to pick the other rank. So it's very convenient to know if the proportion goes your way, right? If you flip a coin and you know it's always landing heads and you want to win money, you're going to bet on the heads. So when we have some knowledge, as in P hat, Q hat, it's a lot easier for us to deal with this. But the problem is if we don't know, then means we have the worst case scenario. The worst case scenario is we have no clue, which means that if we have a choice between success and failure, it's a 50-50 shot, right? So you have to make some investment and it doesn't bail out, right? And so no knowledge means 50-50. Well, what does mean 50-50? It means P hat equals to Q hat equals to 0.5. There's 50% chance of success, 50% chance of failure, right? That simplifies things because then our formula becomes Z alpha over 2 divided by E squared. P hat is 0.5, Q hat is 0.5. So this is really Z alpha over 2 E squared. 0.5 times 0.5 is 0.25. And there's your formula. So if we have no clue what's going on, this is it. So if we have no clue, we look up 98, which means our alpha is 0.02, which means alpha over 2 is 0.01. We look up 0.01 and we get that Z alpha over 2 is 2.326. And so our formula is N equals 2.326 divided by 5%, the whole thing squared, times this. And so our N becomes 2.326 divided by 0.05 squared times 0.25. And again, what we're going to get is N equals to 542. Why? Because 3% of a person is not a person. Doesn't have to be a person. It's a thing, right? If we are testing dice, 3% of a dice is not a die. So check. So let's look at B. And B says this. Now here's the thing. How do we get an estimate for this? Well, there's a couple things we can do, right? If we have no clue, we have this kind of selection. So that's one. We could have prior or historical data. Say we run the survey every month. We can use last month's estimate, especially if the data isn't very volatile. For example, stocks, right? We can use the previous months or previous weeks data to estimate this. We could make an educated guess. Not very good choice, but if you're an expert in the field and you have other data sets that are similar, you can kind of borrow it. Like, for example, we know what happens if there's a large discrepancy between, say, rich and the poor in a country, because we can look at Venezuela or China or North Korea or Russia and see what happens, and then we can apply this kind of adjusted lesson to something else. And we can do a pre-survey of some sort, where we can actually send out a smaller survey just to get an estimate for it. So we send a survey of 100 responses, and we estimate P, and we get the P hat, and then we use that P hat to run this calculation to figure out how big the new survey has to be. And again, there's a bunch of ways to do it. So there's other classes that teach how to actually do and which way is kosher, which not. I'm here just to teaching you how to do addition. So I'm not going to be getting into it. But if we have P this, then we have Q, which is this, which means our formula becomes that. No, our Z is still the same, so that's 2.326 divided by 0.05. This whole thing squared, 0.1, 0.9. I want to bring this up. See the difference between those two numbers? It's about 350 surveys difference. 350 surveys difference, and if you're lucky and say there are $10 a pop, that's $3.5 grand. From I have no clue to I did my diligence and I have some estimates for what P and Q are. 350 surveys. And again, those are small studies. If you look at the political studies, when they're trying to judge, for example, the presidential candidates, those studies have the size of 10,000, 5,000, 4,000, 20,000 people. Shaving off a couple thousand, that's a lot of money. So just keep that in mind when you think about the usability of this class. All right, example 11. This pen, I'm gonna have to glue it together. All right, example 11. Find the minimal sample size required to estimate the proportion within 3 percentage point. All right, well, 3 percentage points. So first of all, we're going to change it to decimal places so we don't know. P hat equals Q hat equals 50%. Why? Because they didn't give us to us, so we're doing the best we can guess, right? Because it says estimate the proportion of young people who apply sunscreen regularly before going out in the sun in the summer. I think you should apply it not before, but like 30 minutes before. But anyways, find minimal sample size required to estimate the proportion within 3 percentage points. Okay, so we don't know what the actual percentage is. We're guessing worst case scenario, right? We're not going to be estimating it. I'm just going to say we don't know. So this is it. All right. So this gives us alpha of 0.1, which gives us alpha over 2 at 0.05, which gives us z alpha over 2 of 1.645. All right. So our n equals to z alpha over 2 divided by e squared times 0.25. What's 0.25? Well, it's p times q, right? But we don't know p and q. So our n is 1.645 divided by 0.03, not 3, 0.03, that's important, squared 0.25. 1.645 divided by 0.03 squared times 0.25. And that will be the answer. And that's it for chapter 7. Again, the whole idea is we're trying to size things up using a small selection by comparison to the size of the population. And we need to figure out, hey, based on the parameters we are inputting, like margin of error and confidence, how many of those do we need to actually test to get the final result? And again, worst case scenario is 50%. So that's it for chapter 7. I will before the semester is over next week or the week after that, I will probably record a chapter 8 just so you guys have chapter 8 available to you, and I will do my final goodbyes and thank you for joining and whatnot next time. For now, this is chapter 7. Good luck. Let me know if you have any questions.